Welcome to our journey into the fascinating world of relativity. Today, we'll break down two of its most mind-bending concepts, time dilation and length contraction. These ideas might sound complex, but with the help of visual storytelling, you'll see just how intuitive they can be. Imagine you're on a train speeding close to the speed of light. What would you experience? How would time and space behave differently for you compared to someone standing still? Let's set the stage for our adventure by understanding why Einstein's theory changed the way we see the universe. Einstein's theory of relativity tells us that the laws of physics are the same for everyone, no matter how fast they're moving. But here's the twist: time and space aren't as rigid as we once thought. They can stretch and shrink depending on your speed. This means that two people moving at different speeds can actually experience time and distance differently. It's a radical departure from our everyday experience, but it's been proven true in countless experiments. Let's dive deeper into what this means for time itself. Time dilation is one of the most famous predictions of relativity. It means that time can actually slow down for someone who is moving very fast compared to someone who is standing still. Imagine two twins, one stays on Earth while the other travels on a spaceship at near light speed. When the traveling twin returns, they'll be younger than their sibling. This isn't science fiction, it's a real effect measured with atomic clocks on airplanes and satellites. But why does this happen? Let's visualize. Picture a light clock, a device where a beam of light bounces between two mirrors. For someone standing still, the light travels straight up and down. But if the clock is moving quickly, the light has to travel a longer diagonal path. Since the speed of light is always the same, this means it takes longer for the light to bounce back and forth. That's time dilation in action, moving clocks tick slower. This simple visualization helps us see why time stretches as speed increases. You might wonder if time dilation affects us in daily life. While the effect is tiny at everyday speeds, it becomes significant at high velocities. For example, GPS satellites orbiting Earth move fast enough that their clocks tick slightly differently than those on the ground. Engineers must correct for this difference, or GPS wouldn't work accurately. Even though we don't notice time dilation while driving a car, it's a crucial factor in modern technology. Now let's turn to length contraction. Just as time stretches for fast-moving objects, space contracts. This means that if you're moving very quickly, distances in the direction of your motion actually get shorter. Imagine you're on that fast-moving train again. Objects outside seem squished in the direction you're traveling. This isn't an illusion, it's a real measurable effect predicted by relativity. Help you picture length contraction: imagine holding a ruler while standing still. Now, if you could somehow run with that ruler at nearly the speed of light, someone watching you would see the ruler is shorter than it was before. The faster you go, the more it shrinks in the direction of motion. This effect only becomes noticeable at speeds close to light, but it's a fundamental part of how the universe works. Length contraction happens because the speed of light is constant for everyone, no matter how fast they're moving. To keep this rule, space itself must adjust. When you move faster, distances in your direction of travel get shorter. This keeps the laws of physics consistent for all observers. It's a strange idea, but it's been confirmed by experiments with particles moving at high speeds in accelerators. Particle accelerators are laboratories where scientists test the limits of relativity. Particles are sped up to nearly the speed of light, and both time dilation and length contraction are observed. The particles' lifetime stretch and the distances they travel shrink, just as Einstein predicted. These experiments provide some of the strongest evidence for relativity's predictions, showing that these effects are not just theoretical, they're real and measurable. One of the most famous thought experiments in relativity is the twin paradox. Imagine one twin stays on Earth while the other travels at near light speed and returns. The traveling twin will have aged less than the one who stayed behind. This isn't just a story, it's a direct result of time dilation. The paradox is resolved by realizing that the traveling twin experiences acceleration and deceleration, breaking the symmetry. Let's picture the twin paradox visually. Imagine two clocks, one on Earth, one on a spaceship. As the spaceship moves away and returns, its clock ticks slower compared to the Earth clock. When the twins reunite, the difference in their ages is clear. This visualization helps us grasp how time dilation works in real scenarios, not just in theory. Relativity isn't just for scientists, it's part of our everyday lives. GPS satellites orbit Earth at high speeds and experience both time dilation and length contraction. Engineers must adjust the satellites' clocks to match those on the ground. Without these corrections, your phone's navigation would quickly become inaccurate. Relativity keeps our technology running smoothly. The speed of light is the universe's ultimate speed limit. Nothing can go faster. This rule is at the heart of relativity. It's why time slows down and space contracts as you approach light speed. The constancy of light speed forces the universe to bend its own rules, leading to the strange but true effects we've discussed. Imagine a train racing near the speed of light. Inside, passengers experience time normally, but to an observer outside, everything on the train appears to slow down. The train itself looks shorter in the direction it's moving. This visual story brings together time dilation and length contraction, showing how both effects work together at high speeds. Science fiction often explores the consequences of relativity. Stories about space travel, time machines, and aging astronauts all draw on real physics. While some tales take creative liberties, the core ideas of time dilation and length contraction are grounded in scientific fact. Relativity fuels our imagination and inspires new adventures. At everyday speeds like driving a car or flying in a plane, relativity's effects are minuscule. But as you approach the speed of light, time dilation and length contraction become dramatic. This is why we don't notice these effects in daily life, but they're crucial for understanding the universe at extreme speeds. Relativity isn't just about fast trains or spaceships, it shapes the entire universe. From the bending of starlight around massive objects to the expansion of space itself, Einstein's ideas help us understand everything from black holes to the Big Bang. Time dilation and length contraction are just the beginning. Black holes are cosmic laboratories for relativity. Near a black hole, gravity is so strong that time slows dramatically, a form of time dilation caused by gravity, not just speed. Space itself is warped and the effects of relativity become extreme. Observing black holes helps scientists test the limits of Einstein's theory. Gravity can also cause time dilation. The stronger the gravity, the slower time moves. This is why clocks on satellites tick faster than those on Earth's surface where gravity is stronger. Both speed and gravity can stretch or shrink time, showing the deep connection between space, time, and the forces of nature. From GPS to particle accelerators, relativity is woven into the fabric of modern technology. Engineers and scientists use Einstein's equations to design systems that work accurately, even when moving at high speeds or in strong gravitational fields. Without relativity, much of our technology would simply fail. Equations of relativity might look intimidating, but their meaning is profound. They describe how time and space change depending on speed and gravity. While we won't dive into the math here, it's important to know that these formulas have been tested and confirmed in countless experiments, making relativity one of the most successful theories in science. Light plays a central role in relativity. The fact that its speed is always the same, no matter how fast you're moving, forces time and space to adjust. This leads directly to time dilation and length contraction. Light's constancy is the foundation of Einstein's revolutionary ideas. The Big Bang Theory, which describes the birth of our universe, relies on relativity. The expansion of space, the stretching of time, and the movement of galaxies all follow Einstein's equations. Without relativity, we couldn't understand the universe's origins or its ultimate fate. Cosmic rays are high-speed particles from space that slam into Earth's atmosphere. Because they move so fast, they experience time dilation and length contraction. This allows them to survive long enough to reach the ground, even though their lifetimes are incredibly short when measured at rest. Muons are particles created when cosmic rays hit the atmosphere. They decay quickly, but because they travel near light speed, time dilation allows them to reach the ground before decaying. This real-world example shows relativity in action, confirming Einstein's predictions. Astronauts on the International Space Station move fast enough to experience tiny amounts of time dilation. Over long missions, their clocks tick just a bit slower than those on Earth. While the effect is small, it's measurable and must be accounted for in precise experiments. Relativity affects how we communicate across vast distances. Signals sent between Earth and distant spacecraft must account for the stretching and shrinking of time and space. Engineers use relativity to ensure messages arrive accurately, even across millions of kilometers. As we explore deeper into space and develop faster spacecraft, relativity will become even more important. Understanding time dilation and length contraction will help us plan missions, design technology, and perhaps one day travel to the stars. Teaching relativity through visual storytelling makes complex ideas accessible. By using simple analogies, animations, and real-world examples, educators can help students grasp time dilation and length contraction. Visual learning brings Einstein's ideas to life. Artists and filmmakers often draw inspiration from relativity. The bending of time and space sparks creativity, leading to stunning visuals and imaginative stories. Relativity bridges the gap between science and art, showing that the universe is as beautiful as it is mysterious. Relativity challenges our understanding of reality. If time and space are flexible, what does that mean for our experience of the world? Philosophers have debated the implications of relativity for over a century, exploring questions about perception, reality, and the nature of existence. Relativity sets a limit on how fast information can travel. Nothing, not even a message, can go faster than light. This rule shapes everything from communication technology to our understanding of causality in the universe. By showing that time and space are not absolute, relativity forces us to rethink what's real. Our everyday experience is just one perspective among many. The universe is more flexible and interconnected than we ever imagined, and relativity is our guide to understanding its true nature. The expansion of the universe is a direct consequence of relativity. As space stretches, galaxies move apart and time itself evolves. Observations of distant galaxies confirm Einstein's predictions, showing that relativity shapes the cosmos on the largest scales. Relativity introduces the concept of spacetime, a unified fabric that combines space and time. Massive objects like stars and planets bend this fabric, creating gravity. Time dilation and length contraction are natural consequences of this flexible spacetime. Relativity is a cornerstone of modern physics, but it's not the end of the story. Scientists are searching for a theory that unites relativity with quantum mechanics. The quest for a deeper understanding continues, driven by curiosity and the desire to unlock the universe's secrets. Einstein's theory of relativity is a testament to human curiosity. By questioning the nature of time and space, scientists have uncovered truths that challenge our imagination. Relativity reminds us that the universe is full of surprises waiting to be discovered. Einstein once said, "Imagination is more important than knowledge." Relativity was born from thought experiments, imagining what would happen if you chased a beam of light. This creative approach led to discoveries that changed the world. Relativity's success is built on collaboration. Scientists, engineers, and thinkers from around the world have tested, refined, and applied Einstein's ideas. This spirit of teamwork drives progress and helps us unlock the mysteries of the universe. The next generation of scientists will build on relativity's foundation. By exploring new frontiers and asking bold questions, they'll continue to expand our understanding of time, space, and the universe. The adventure is just beginning. Relativity isn't just a scientific theory, it's a new way of seeing the world. By revealing the flexibility of time and space, it invites us to question our assumptions and embrace the unknown. Our journey through relativity is a journey of discovery, wonder, and awe. The beauty of relativity lies in its simplicity and power. With just a few principles, it explains some of the universe's most mysterious phenomena. Relativity shows us that science is not just about facts, but about seeing the world in new and unexpected ways. Exploring relativity is like exploring a new world. Each discovery opens up new questions and possibilities. The spirit of exploration drives us to push the boundaries of knowledge and venture into the unknown. Einstein's legacy lives on in every scientific breakthrough that builds on relativity. His curiosity, creativity, and determination continue to inspire generations of thinkers. Relativity is more than a theory, it's a testament to the power of human thought. As we conclude our journey, remember that relativity offers a new perspective on reality. Time dilation and length contraction show us that the universe is more flexible and surprising than we ever imagined. By embracing these ideas, we open our minds to new possibilities and a deeper understanding of the cosmos.